next one, which is the common gate amplifier. Okay. Now, for the case of a common gate amplifier, where is my input that has been fed and where is the output that will be taken out? For this, where is my input given and where is the output that is taken? I'll just come around and later on. So where is the input that has been given and where is the output that is taken? Source is for the input. Source is the input. Okay, so what about the output?
It's actually symmetric, sir.
It is actually symmetric, but there is one particular problem that I have given during the activity. Do you all remember that? Only very few people had addressed it. The second part of your problem, the last problem, where we had a given circuit which is almost like common gate, but the point is that we had interchanged this. We had fed the input to the drain and we had taken the output from the source. Okay, but normally for a common gate, we actually have to feed the input to the source and we'll take the output from the drain. Okay, but when I do the other way, like this, we found that the gain of the circuit falls less than 1. Okay, so which doesn't serve for any purpose. Is that clear? And that is a conclusion that we were expecting from you to get it out of the circuit. Clear? So now in general, for a common gate, we have the input that has been fed to the source and the output is taken from the drain. So based on this statement, let me try to draw the circuit. So I just want you people to derive the gain expression for this. So the gain is always GM times R out. If you could be able to say what is the GM and what is the R out, you are good enough. And also we will try to identify the input impedance of the circuit, just because the input impedance is no more infinity. Okay, yeah. So what is this capital GM of the circuit? 1 by GM is the transconductance. GM prime. Do you all agree with it? I'll just give time, you work it out and tell me what is my capital GM of the circuit. Otherwise you work out, you will not practice. Okay. So during this capital GM computation, what I do generally, I just short this output to the ground and look for this I out, right? So now what kind of current can flow around this particular path? What is that I have here? So is there any current that flows from through the RD? No. Why? Because when I'm trying to translate this RD in a small signal, the VDD goes to ground. Okay. Here again, the other end of my drain resistance is also connected to the ground. So no current can flow through this RD. So no need to consider this RD at all. So if that is the case, how will I expect this I out from where it can originate from? Now, I am not expecting you people to be like this. So basically the gate potential is a DC, so due to which I connect the ground and the source is already connected to my Vin. So I retain this value of Vin just because when I try to compute the GM, what I do is that I fix my Vin. Okay. So now based on this polarity that I have defined for this VGS, I first define the current direction that flows between the drain and the source. Okay, which is GM VGS, and I also have this R naught. Yeah, so now what is the relation that I have for this capital GM? So one can even expand the value of VGS as VG minus VS, and we know that the value of VG is basically 0 just because it has been grounded. Okay, and what is connected to my source potential is just the value of Vin. So I just fix this Vin. So in the place of VGS I have minus Vin, right? So the current that I can expect out of this is nothing but this current plus this current. So I can write this I out as a summation of, yeah, I forgot one more thing. Do I miss something else? Yeah, body effect. So again that current also has to follow the same current direction that I have defined for here. So I forgot that. So it would be GMB, VBS. Okay, so there are 3 current components that adds up to this I out. Okay, yeah. So again you can expand this VBS as VB minus VS. What is connected to the body? Ground. So we end up having the same formula. Okay, so we can actually combine this current source with this current source as GM plus GMB. Okay, So we can go ahead with this GM prime itself. Yeah. So I would have something like GM prime Vn is one of the current component, or combining both the current components, and there is also a current that flows across or flows through this R naught. What is that current? Yeah. So that would be Vn by R naught. Okay. So having got this Vn in one end, I can just pull out this Vn and I can divide this in order to define my capital GM. So my capital GM is basically I out by Vn, and that is equal to GM prime plus 1 by R naught. Okay. So again, one could expand this GM prime as GM plus GMB. Okay. So I'm just using the short notation. Okay. So now that I've got this, what is my output resistance here? At least that. Yeah, RD in parallel with? Sure, right? No doubt in it. Okay, fine. Now, as I said before, this circuit has a value of Rin which is finite. Okay. In all the previous circuit, we always try to feed our inputs to the gate. So due to which we always had this small signal input resistance as infinity. Whereas in this case, is the small signal input resistance is still an infinity? No. Why? Just because we are looking into the source terminal. Now what is the formula of it? I have a drain resistance, I am looking through the source. So what happens with the drain resistance? Try to recollect. It decreases. By what factor? Yeah, so there is a body effect, so GM prime R naught. So we'll just begin with it and we'll try to reduce that formulae. Okay, we will not derive it here because we have already done this. So I know that approximately the drain resistance would be reduced by a factor of 1 of GM prime R naught. And then if I think, scratching my head, I know that there is something like 1 plus at the beginning of this GM prime R naught. So I remember that. And also at the top, it is not only the drain resistance that get reduced, but also the R naught will also get reduced. Okay, so due to which I have something like R naught plus RD divided by this entire 1 plus GM prime R naught. Okay, so you see the whole of this formula is been taken out of our mind just by knowing that if I look through the source, the resistance that I am seeing will be reduced. Okay, so just purely with that concept, we have got down to this expression. Okay, so if you really want to know how this expression have arrived, you have to go and watch the output impedance video that I've uploaded. Okay, so now I'll just try to add a small bit of spice into this circuit, and let us try to do the same computation on this circuit. Okay. Yeah, so now the first question, what is the value of Rin? Rs plus whatever the impedance that we wrote earlier, nothing. Okay, so it's a pretty straightforward. We know that what is the impedance that we have seen earlier, okay, which was R naught RD divided by this 1 plus GM prime R naught. Okay, that was the previous expression that we have got. Now this entire resistance was being added in series with this Rs. So due to which you add this Rs plus this whole quantity that I had earlier. Okay, so that's it. We have done with it. Okay. Now, what about this capital GM? Capital GM, I think you have to work it out. Okay, what I do is that I'll just try to write the final expression because we are running out of time, and due to which I'll just write down the final expression. Is that fine? Okay, so there is one small exercise problem. I thought I'll do at least that. Yeah. So the final expression of this turns out to be GM prime R naught plus 1, and we have Rx at the bottom. Okay. So if you compare the same value where Rs is equal to 0, we had this GM where it was defined as GM prime plus 1 by R naught. That was the impedance that we had. Okay, so which can also be written as GM prime R naught plus 1 divided by R naught. So right now only this bottom part R naught is being replaced with Rx. Now what is this Rx? What are the impedance that I am looking from this output? Okay, so that value is Rx, and we were using, even right from common drain, we were using the same notation. Okay, yeah, so it is R naught plus Rs plus GM prime Rs R naught. Okay, yeah. So in the place of R naught that we had before, only at the bottom, that has been replaced with the whole lot of expression for this Rx, okay? Is that is clear? That's the only difference. Now, what about the R out? Yeah, when I look up, what is the resistance I'm seeing? RD. And when I look down, what is the resistance I'm seeing? Rx. That is a quantity that I've already made, right? So it is just RD in parallel with Rx. As simple as that. You know that you have got the value of GM, you basically got the value of R out. You have to multiply both these quantities in order to get the gain expression, okay? Now what I do is that let us try to compute a simple exercise. So this is an ideal current source and that you are trying to fix in, and you are trying to apply an input and you are tapping the output over here. Now what is the input impedance and what is the voltage gain? Now I have asked for input impedance, so I have replaced with an ideal current source. So what about the impedance posed by this current source, or what happens when I translate the current source into a small signal model? Yeah, it becomes an open circuit, okay? So now what happens in that case? But again, R naught was connected to our drain resistance, right? Right now the drain resistance is infinity. So R naught, when it gets added to it, it's again an infinity, okay? So if you could able to recollect that when I had a resistance RD here, we ended up having the value of Rin as something like R naught plus RD divided by this GM prime R naught, right? So we basically got down to that. But what has happened is that the value of RD has right now become infinity. What happens to the entire formula? Infinity. So infinity divided by anything would, apart from infinity, it is equal to infinity itself, right? So we have got the value of Rin that is equal to infinity. What about the voltage gain? Okay, so I think the formula that we had for this is 1 by R naught, and then yeah, R out is, yeah, but basically there is nothing but R naught itself, right? We don't have any resistance here at the bottom. Source doesn't have any resistance. Okay. So this particular example would help us to lead our way into a cascade amplifier. Okay, it's some sort of help that we'll get out of the circuit. What type of amplifier this M1 mimics? What is the type of amplifier this M1 mimics? Is it a common source or common drain or common drain, right? Yeah. So it mimics a common drain because the output of this M1 is fed as an input to my M2 transistor. Okay. So if I clearly see here, the input is here, the output is here. Okay. Yeah. So now how would we compute this entire expression? I have given that gamma is equal to 0 but lambda is not equal to 0. Now one thing that we can do is that if I could able to find the Thevenin's voltage and the resistance across this point, okay. So across this particular point, then I can solve with the way that we were doing this solution well before. So what I do is that I will just take only this part of the circuit, try to identify. Now for this, what would be the Thevenin's equivalent voltage and the resistance that I would get out of the circuit? So when it comes to common drain, I said I'm looking for the output node. So what is that impedance that I see across the output node of it? Where is my output of my common drain? It is across the source terminal. So that source terminal possesses an impedance whose value is 1 by GM, 1 by GMB in parallel with R naught. So we know how all of these three resistances are connected to each other, right? So apply those. So what I do is that I know that my V in, which was at the gate, okay, and there is a resistance between this G and the source, and the value of this resistance is 1 by Gm, okay, and what else? What are the other resistance we have is R naught. So R naught is fault across the source and the drain is basically connected to the ground. So I just connect it here, and even my 1 by Gm B is also falls in parallel. Okay, but I'm not going to look up. Okay, it is only the circuit looking from the bottom. Okay, you see, all of this Thevenin's equivalent circuit is completed only for this dotted boxes. Okay, don't ever worry about the top structure. Now, how will I compute this voltage? Yeah, so the V in equivalent is nothing but this resistance, right, or V in into this impedance, which is R naught in parallel with GMB, divided by 1 by Gm less. Okay, so now that I have got this equivalent voltage, okay, Thevenin's equivalent voltage, how will I extract the Thevenin's equivalent resistance? Yeah, but we know the answer for it. I'm looking into the source, that's it. And whenever I try to compute the resistance of the source terminal, what I do is that I will short my V into the ground. So what is left over? How are these? All three are in parallel, 1 by Gm, 1 by GMB and R naught. All of these three resistances are in parallel. So computing the value of R equivalent is pretty straightforward. All of these impedances has to be in parallel. So okay, so what I can do is that I can just replace the bottom structure with a resistance R equivalent whose value is defined here, and the value of V in equivalent whose value is defined here. Okay, and we have already discussed about the gain expression for this, right? So utilize that and try to extract the gain expression of it. Okay. So in the last class we have been looking at this common gate amplifier, right? So I'll just write down only the final results of these things. So when we had this lambda that is equal to 0 and gamma that is equal to 0, we had a GM value which is equal to GM1, okay, or if you want, I will just draw the structure. Yeah, so in this case, if I have this lambda factor that is equal to 0 and gamma factor that is equal to 0, so obviously the GM that I would get out of the circuit is just GM1 itself, okay, and obviously the R out would then be equal to RD, okay. Now if I go for lambda that is not equal to 0, but still, okay, we'll just go with gamma that is also not equal to 0. Then for this type of circuit, we had this GM to be equal to GM1 plus 1 by R naught with a prime, right? So this was the expression that we got the moment we had both these assumptions being taken off, okay? And similarly, for this R out, what happened is the moment we leave out this lambda factor, we ended up having RD in parallel with R naught, okay? So again, I'll just use the suffix of 1 for both ROs. And later what we did is that we had a resistance being plugged here with a value of RS. The moment I plugged this resistance RS, again what happened is that we had a different expression for the GM and R out, right? So what was that expression of GM that we got the moment I plug in this? So it was GM prime R naught plus 1 divided by Rx. So again, Rx is always the same quantity. Please try to remember that. So I hope that no problem with this substitution of Rx, right? You know what expression you would get it. Yeah. So now obviously the output resistance also changes just because of the inclusion of Rs. So that has become something like Rd in parallel with Rx. Okay. So there are a few changes that are happening. Now one could obviously compare our results with, for the top case, I can compare these results with a CS amplifier with a resistive load, whereas this particular result I can compare myself with a CS amplifier with source degeneration. Okay. Yeah. So I think you might be knowing the answer for this, for the top one. If at all, if I'm comparing with this for the CS amplifier, I would have got the GM to be equal to minus GM, right? And the Rout would have something like RD in parallel with R0. Okay, so there is a certain difference that I would get between the CS amplifier and the common gate amplifier. And when I compare this guy with source degeneration, then my GM has a certain small difference in it. So what was that? So we had something like GM at the top. Yeah, R0. Okay. Yeah, I guess, yeah, GM R0 divided by Rx is what I would have got, I guess, right? Yeah. So, and then the value of Rout is same, RD in parallel with Rx. Okay, so there is a certain difference that we have across these structures. Okay. Now, what I do is that let us try to analyze the large signal, because that particular part I didn't teach in the last class, so I'll just try to work around this large signal behavior of this circuit. Let me try to draw this V out versus V in graph. And what happens the moment initially I start raising this value of V in? So when the value of V in is low, how will I define my output to be? So what happens the moment I have V in that is equal to 0 is that I have VGS value which is non-zero or 0. It's a non-zero and it's a very large value, right? Just because currently I've brought this node towards the ground. So I have a potential difference across this VGS which drops across, let me remove this RS. Why to include that? Okay, so let me try to deal without RS. Okay, so whatever the value of VB that I have entirely falls across this VGS as it is when I have the V in that is equal to 0. Now in that case, how will I define my output? Is there an existence of current? Yes, obviously there is an existence of current and the value of that current would be large. So that is for sure. So how will I read the drop across this V out then? Yeah, it is VDD minus ID times RD. So since the value of ID currently that I have for this value of V in is large, what happens is that my value at V out will be small just because the ID value is very large. Okay, so basically the drop across this RD is high, due to which I will begin with this particular quantity here. Okay, now this is my value that I have, and this ID I cannot fix it something like that just because the ID also changes the moment I start varying my input. So let me just have a simple name or simple label for this. Let me label it as VO1. Okay. Now, in which region I'll be operated in? Saturation, linear. Why? Because my drain to source potential is small. That is what I mentioned in the graph in the y-axis, right? So this VO1 is nothing but my V out value, and that is quite smaller. And when I have a large value of VGS, when I compare this large value of VGS with respect to the VDS, obviously the VDS value is small right now currently. Okay, so due to which, during the initial stages, my M1 would be in the linear segment or in the linear region. But what happens after this? Which region I have to enter in? Okay, so what is happening is that I'm trying to increase the value of V in, due to which what is happening to the value of VGS that I have? Reduces. What is happening to the current? That also decreases. What is happening to my V out? Increases. So when I increase the value of V in, the V out is rising. Okay. Now what is happening is that the value of this guy is keep rising, and in turn my VDS value is kept rising when I try to increase the value of V in. Okay. Or in short, my VDS is getting larger when the VGS value is getting smaller. Okay. Now which region I would end up? saturation, right? Yeah. So there is a particular point at which what would happen is that the VGS value is stepping down and my VDS value is stepping up. Okay. So previously I was in linear, and when I step this, both these values would then meet each other, and we call that as an edge of saturation. Beyond which, if I further reduce the value of VGS, my VDS value would keep rising. Okay. So I'll be entering into the saturation regime. Okay. Yeah. So from the linear, I just get into the saturation regime. So in this particular case, let me label this one as something like V in 1 or some sort of value. Okay. Yeah. And in this case, my transistor M1 would enter into saturation regime. Now, what happens after this as I keep increasing the value of Vn? Yeah. So as I increase the value of this Vn, I'm not providing enough value of VGS here. So at a particular point, what happens is that this value of VGS that I have certainly reaches the value of VDH. Okay. So let me mark that particular point over here. It is written as VDH. Okay. Now at that particular point, what happens is that my transistor M1 gets into cutoff. Yeah. So in that case, what would be the value I would get out of the circuit? It will be equal to VDD. Okay. Yeah. Hope that there is no doubt in it, because the current becomes 0 in that case. So the Vout would then be strictly equal to our VDD itself. Clear? Yeah. So this is our Cara, and in this case, I have this M1 into cutoff regime. So as you could able to see, always we travel either from cutoff saturation to linear, or even when we go in the reverse direction, we are making sure that we are starting from linear, getting into saturation, and then getting back to our cutoff. Okay. So there is no relation that I could jump from linear to cutoff. Okay. I always pass through the saturation. Clear?